Have you ever seen a small triangle in a math problem and wondered what it was doing there? That symbol, delta, is the Greek letter delta. While it might look a little intimidating at first, it is actually one of the most helpful symbols you will encounter in your mathematical journey. Think of it as a secret code that unlocks deeper understanding. In the world of mathematics, delta often stands for one of two very important ideas: change. In the world of mathematics, delta often stands for one of two very important ideas: the discriminant. Both of these concepts help us solve problems and see relationships between numbers more clearly. Understanding delta begins with seeing it as a shorthand for a simple question: what is the difference? If you started the day with 5 apples and ended with 2, the change is 3. We could represent this change using delta. This idea of measuring a difference is fundamental. It is not just about counting apples, it applies to temperature. It is not just about counting apples, it applies to speed. It is not just about counting apples, it applies to distance. It is not just about counting apples, and so much more. By giving this concept its own symbol, mathematicians created a powerful tool to discuss and calculate how things vary, a core part of algebra. By giving this concept its own symbol, mathematicians created a powerful tool to discuss and calculate how things vary, a core part of calculus. By giving this concept its own symbol, mathematicians created a powerful tool to discuss and calculate how things vary, a core part of science. This dual role is what makes delta so interesting. On one hand, it is a straightforward label for change. On the other hand, it takes on a very specific, almost magical role when we dive into certain types of equations. Specifically, in quadratic equations, those with an x-squared term, delta gets a special formula and a new name: the discriminant. Here, it helps us discriminate, or tell the difference, between the types of answers an equation might have. It is like a crystal ball that predicts the future of our math problem. Now, let us zoom in. On one of delta's most famous roles, the discriminant in quadratic equations. A quadratic equation is any equation that can be written in the form ax squared plus bx plus c equals 0. The letter a, the letter b, the letter c are just numbers, or coefficients. For example, in the equation 2x squared plus 5x minus 3 equals 0a is 2b is 5c is negative 3. Solving these equations means finding the value, or values, of x that make the equation true. Sometimes there are two solutions, sometimes there is only one, and sometimes there are no real solutions at all. How do we figure out which case we are dealing with without going through the entire solving process? This is where our hero, delta, comes in. For quadratic equations, delta is calculated using a special formula. Delta equals b squared minus 4ac. You simply take the numbers of b and c from your equation and plug them into this expression. You take the b value, square it, and then subtract 4 times the a value times the c value. The final number you get for delta is the discriminant, and its value holds the secret to the solutions. Let us use our example, 2x squared plus 5x minus 3 equals 0, to see this in action. Here, a equals 2, b equals 5, c equals negative 3. Now we plug these into the discriminant formula. Delta equals b squared minus 4ac. This becomes delta equals 5 squared minus 4 times 2 times negative 3. First, we calculate the parts. 5 squared is 25. Then, 4 times 2 times negative 3 is negative 24. So our equation becomes delta equals 25 minus negative 24. Remember that subtracting a negative number is the same as adding, so we get delta equals 25 plus 24, which equals 49. The value of our discriminant is 49. So we have a number, 49. What does it mean? This single number is incredibly powerful because it tells us everything we need to know about the roots, or solutions, of our quadratic equation before we even find them. The value of delta, whether it is positive, negative, or 0, discriminates between the possible outcomes. It is a quick diagnostic tool that saves us time and gives us a roadmap for solving the problem. In the next section, we will see exactly how to interpret this number and what it reveals about our equation's hidden answers. So, as we explore this friendly Greek letter, remember its two main jobs. It is the symbol for measuring the difference between two values, a concept we use every day without even thinking about it. And it is the key to unlocking the secrets hidden within quadratic equations, telling us exactly what kind of solutions we should expect to find. The number we get from the discriminant formula, delta equals b squared minus 4ac, acts like a traffic light, guiding us to the right kind of solution. There are three possibilities for delta's value, and each one points down a different path. The first path is when delta is a positive number, delta greater than 0. This is what happened in our earlier example where we found delta equals 49. A positive delta is great news. It tells us that the quadratic equation has two distinct, real solutions. This means there are two different numbers you could plug in for x that would make the equation true. The second path occurs when delta is exactly 0, delta equals 0. Let us imagine an equation like x squared minus 6, x plus 9 equals 0. Here, a equals 1, b equals negative 6, and c equals 9. When we calculate delta, we get delta equals negative 6 squared minus 4 times 1 times 9. This simplifies to delta equals 36 minus 36, which equals 0. When the discriminant is 0, it tells us that there is exactly one real solution. This is sometimes called a repeated root, because it is like the two solutions have merged into a single point. So if you get a delta of 0, you know you are looking for just one special value of x. The third and final path is when delta is a negative number, delta less than 0. Consider the equation x squared plus 2x plus 5 equals 0. In this case, a equals 1, b equals 2, and c equals 5. The discriminant would be delta equals 2 squared minus 4 times 1 times 5, which is delta equals 4 minus 20, or negative 16. A negative delta tells us something very different. There are no real solutions. This means there is no number on the standard number line that you can substitute for x to make the equation true. In more advanced math, you learn about imaginary numbers to handle this case, but for introductory algebra, it simply means no real answer exists. While its role as the discriminant is famous, delta's original and more common meaning is simply change or difference. This is perhaps the most intuitive way to think about it. Whenever you see a delta in front of a variable, like delta x or delta y, it is a compact way of writing the change in x or the change in y. For example, if you are tracking the temperature, you could write delta t to represent the change in temperature between 2 points in time. If the temperature was 15 degrees Celsius in the morning and is 22 degrees in the afternoon, then delta t equals 22 minus 15, which is 7 degrees Celsius. This concept of change is absolutely essential in many areas of math, especially when we talk about slope. The slope of a line tells us how steep it is. We calculate it by measuring the vertical change, the rise, and dividing it by the horizontal change, the run. Using our new symbol, the formula for slope is written as m equals delta y divided by delta x. This reads as slope equals the change in y divided by the change in x. It is a much more elegant and professional way to express the idea than writing it all out in words every single time. Let us look at a simple, real-world example. Imagine you are on a road trip. After 2 hours, you have traveled 120 miles. After 5 hours, you have traveled 300 miles. We can find your average speed during that interval using delta. The change in time, delta t, is 5 hours minus 2 hours, which is 3 hours. The change in distance, delta d, is 300 miles minus 120 miles, which is 180 miles. Your average speed is the change in distance over the change in time, or delta d divided by delta t. So, your speed is 180 miles divided by 3 hours, which is 60 miles per hour.